So we started talking about hypothesis testing, and we said if we have a population and we want to basically check a claim or hypothesis about the parameter of the population, we can implement a hypothesis testing procedure and then see if our claim about that parameter is correct or not. Basically, we have two types of hypothesis testing. One is two-sided, the other one is one-sided. Okay? For two-sided, mu is equal to one parameter, one value, and this is called H null, and alternatively, we have mu is not equal to that number. For one-sided, we have either less than or greater than, depending on what we want to evaluate. Sometimes we care about only upper bound. Sometimes we care about only lower bound. That's why we have one-sided hypothesis testing. And we said conventionally, we always use equality for H null. Okay? And also, for one-sided, when we have any claim or desire, we put it in H alternative. Okay? We had two basically phases. One was design. In the design, we state our null and alternative hypothesis. And then what is the sample size? What is the significance level, which is alpha, or 1 minus confidence level. We define the test statistics based on the condition that we have. For example, whether variance is known or unknown. Are we testing mean or variance? These are basically the criteria we should consider. Then last step is to find the distribution of test statistics under H null and then find the rejection region. In this case, for example, if we want to test mu is equal to 50 or not, then our test statistic is basically I don't know why it's not working. Our test statistics is Z naught or a standard. Okay. Our test statistic is basically this guy, which is the standardized version of our X bar. And then we know that if null hypothesis is correct, this follows the standard normal distribution. And the rejection region, as we showed before, is Z alpha over 2. If the absolute value is greater than Z alpha over 2, then we reject H null. Okay? And then we use it by using, we observe the sample, as you can see. We calculate our test statistic and we compare it with the threshold. In this case, it's not greater than threshold, then we do not reject H null. So the first set of hypothesis testing that we discussed was for mu of a normal population and when variance is known. In this case, this is always null hypothesis. Alternative could be two-sided or one-sided, and these are the corresponding rejection regions. Okay? For one-sided, we just replace this Z alpha with alpha, and then if it is greater than, it should be greater than. If it is less than, this guy is less than minus Z alpha. Okay? Any questions on hypothesis testing, the concept? Yeah.
You have a preference, like you want to minimize the average or whatever, so you want to use a less than for the alternative. If you fail to reject a null hypothesis, does that mean, is that like a good thing? That's what you want?
So usually you put what you claim or what your desire is in H alternative.
Right.
If you fail to reject, it's not a good thing in that case. For example, you want to basically your waiting time to be less than 10. Okay, so you put it in H alternative. What is your H null? Mu is equal to 10. Okay, and we said implicitly this is greater than equal to 10. Okay. So if you fail to if you reject H null, then what happens? Your waiting time, mean waiting time, is less than 10, which is a good thing. Okay, if you reject H null, then this is H alternative. Okay? But if you fail to reject H null, means what you said in H alternative is not true. Okay? Okay. So we had a couple of examples, and I finished this example. I just want to make sure. I solved it, am I right? You got the value. Yeah.
Reject H null. Does the same logic follow that we can't say that that proves that H alternative is true? It just means that H null is...
No. We just say we cannot accept H null. Okay. Which means, because based on this sample, that could happen. You know? So there are three ways for evaluating your hypothesis test. One was based on these critical regions. The second method is based on confidence intervals. Okay? So what you do if you are evaluating a two-sided hypothesis test, you construct a two-sided confidence interval using X bar. Okay? Then you see if mu0 belongs to this confidence interval or not. If it belongs, you cannot reject. Otherwise, you reject that. Okay? And this is for the lower side, and this is for the upper, basically, one-sided hypothesis testing. Again, if the confidence interval does not include mu0, then we reject H null. And actually, these two are one-to-one correspondent. Let me just use one of them. Let's use this guy to show that these two methods are actually the same thing. So we reject H null if your mu0 does not belong to this interval, which is X bar minus Z alpha and infinity. Okay? What does it mean? It means mu0 is less than X bar minus Z alpha. Okay? Which is that true? Just want to make sure. Yeah. So it's Z alpha times this guy is less than X bar minus mu, and then I divide it by X bar minus mu divided by standard error. This is what? And this is mu0, sorry. What is this guy? Z0. So if Z0 is greater than Z alpha, we reject H null. If I go back to this table, you can see mu greater than mu0, the critical region Z0 is greater than Z alpha, which is exactly the same thing here. Okay? So these two are equivalent. Is it clear? Any questions so far? Okay. So the same example that we had, use confidence interval method to evaluate the hypothesis. Remember the hypothesis was mu equal to 75 and mu greater than 75. Okay, so what should we do? We know that the X bar n is equal to 25, X bar is 79.25, and sigma is basically 8. So I need to find this confidence interval. And by the way, alpha is 0.05. in this case is 79.25 minus z of 0.05, 8 divided by square root of 25. So if you calculate this, your if I can find it, hopefully. Actually, I don't have it here. But 79.25 minus 1.645, 8 over 5. Can you quickly calculate this one using calculator? What is it? 76, sorry. Okay, point? 62? Okay. So this is basically your confidence interval is from 76.62 to infinity, 75. Is what? Does not belong to this confidence interval. Therefore, reject H null. Okay? That's the same basically conclusion that we drew last time. So it doesn't matter which method you are using. The conclusion at the end of the day should be the same. Any questions? Usually, yeah, actually, we want alpha to be basically a small. Usually, we go with 0.05 or 0.01. These two values are very common in practice, and I'll tell you today, actually, in next few slides, you will see what is the meaning of alpha and what does it actually imply. Okay, but usually we go with the small values. It should be between 0 and 1, but nobody use alpha equal to 0.5. Okay, it's sort of like error. Any other questions? You good? Is it too easy? No, actually, it depends which one. It's like having a measure in one domain or another domain. That's it. It's just like how comfortable are you in terms of calculating this one or the other one. That's it. Okay, p-values. How many of you have used p-values before? Raise your hand. Okay, good. So p-value is the third method for evaluating or testing your hypothesis. Okay? The definition says the smallest significance level that would lead to the rejection of the null hypothesis. To be honest, every time that I read this definition, I get confused what it's talking about. But that's the definition. Probability, how we can calculate that? Probability of obtaining a tested statistics at least as extreme as the one observed. Given this sign here means conditional probability, given H null is true. Okay? I will show you what this guy means, but let me say what we do with, how we basically evaluate our hypothesis testing using p-value. If p-value is less than alpha, so you have one alpha, which is confidence level, then you reject the null hypothesis. Okay? That's how we use it. But what does it mean exactly? And why this is exactly the same as, so basically saying p-value less than alpha is the same as saying this criterion or confidence interval. Why this is the case? So let me show you first what does it mean when we say probability of obtaining a test statistics at least as extreme as the one observed. So here is one example. Mu is equal to mu 0, and it's one-sided. Mu is greater than mu 0. The test statistics is x bar minus mu 0 sigma divided by square root of n. As you can see, it says obtaining a test statistics. So what is the test statistic? Is z, okay? Standard normal distribution in this case. So obtaining a test statistics, okay, at least as extreme as the one observed. So a test statistics at least as extreme as the one observed. This is the one observed. So we observe this value, and we want to calculate probability of your test statistics is greater than the observed value. Okay? And when we are talking about extreme, we are talking about the sign of this inequality. This says greater than, this is also greater than. If it is less than, this is less than. So basically, probability of z greater than z0 given h null is true. H null is true means what? Mu equal to mu 0. So basically, if I want to translate this expression here to a mathematical expression, it's going to be probability of your test statistics greater than z0, which is the observed one, given mu is equal to mu 0, which is h null is true. Does it make sense? You see the difference? I mean, the relationship? Okay. Now, so given mu is equal to mu 0, this is called p-value. And this is easy to calculate. Why? Because this is standard normal distribution. Then you can easily find probability for that. In this case is 1 minus phi of z0. Why? Because it's 1 minus phi of, 1 minus probability of z less than equal to z0. Okay, given mu is equal to mu 0, which is 1 minus phi of z0. Okay, this is how to calculate. But now the question is why this p-value less than alpha is the same thing as saying z0 is greater than z alpha. Why? Because you remember, if I have this alternative, this is critical region. Okay? Now I'm saying if p-value is less than alpha, okay, reject h null. This one also says reject h null. So these two are equivalent. Why this is the case? It's actually very simple. As I said, this is the rejection region. And here is basically the reason. So rejection region is what? Z0 is greater than Z alpha. Okay? So if I want to use this Z distribution, let's call this Z alpha. So the probability after this guy is what? Is alpha. So Z0 is greater than Z alpha. What does it mean? It means your Z0 is on the right side of your Z alpha. Does it make sense? Your Z0 is on the right side because Z0 is greater than Z alpha. Now, what is p-value? Let's go back to definition. Probability of Z greater than Z0. So this is Z0. Probability of Z greater than Z0 is what? Is, yes, exactly, is this area. Okay? You agree? This is called what? P-value. Now you compare p-value with alpha. Which one is bigger? Your alpha. So your p-value is smaller than alpha. So when your p-value is smaller than alpha, it implies that your Z0 is greater than Z alpha. That's why they are equivalent. Okay? Does it make sense? And as you can see, this is p-value. This is alpha. P-value less than alpha is the same as saying Z0 is greater than Z alpha when we reject H null. Any questions? Is it clear? It's very important to know the concept of p-value. I'm sure that most of you have used it before, but many of you didn't know why p-value less than alpha we should reject H null, which is very important to understand why. And go back to your question. Now I have three methods. Which one is easier to use? P-value. Why? Because it doesn't depend on the value that you get, has nothing to do with basically your type of hypothesis testing. So it's general. Okay? If it is on the mean, you can get a p-value. If it's on variance, you can get a p-value. So it's some number between 0 and 1, and you can compare p-values across different hypothesis testing. Okay? So that's why most of people, especially in statistics and mathematics area, prefer to have p-value, use p-value. Any other questions? Are we good? Okay. So now how we can calculate p-value? These are the equations that we use for calculating p-value. If this is two-sided, that's the equation. For one-sided, greater than, you can see this is alternative. This is the equation. For one-sided, less than, this is the equation. And as I said, p-value less than alpha, we reject null hypothesis. Any questions? Okay. This is one example. Actually, we solved this example before using regular test statistic. Now, I give you a couple of minutes to calculate p-value for this example. So if you remember, this example was mu equal to mu 0, and alternative was, so mu is equal to 50, and the alternative was mu is not 50. And that's the equation for two-sided. So what's the conclusion? Reject or not reject? What is the p-value? Anybody got it? Rejected because of what? Any number for p-value? Nobody? You don't have the table? Less than 0.01. Yep, it's about right number. Okay, so for p-value, we need to find first observed statistic, which is x bar minus mu 0 divided by standard error. In this case, our x bar is 51.3 minus 50 divided by 2, and sample size is 25. And this gives me 3.25, I guess. Is that correct? Yeah. So p-value is 2, 1 minus phi of 3.25. If you calculate this from table, then it's 0.0012. This is less than 0.05, therefore reject H null. Therefore, the mean is not equal to 50. Okay? That's exactly the same conclusion as if you use basically the regular critical region method or confidence interval method. Okay, any questions? Is it clear? Another example is this guy, and we want to know, we want to use basically p-value method to test this hypothesis. This is one-sided, and therefore our p-value is, if I go back, it's 1 minus phi of, is mu greater than mu 0. This is basically the alternative. So it's 1 minus phi of 0. It's 1 minus phi of z 0. So what is z0? Based on this guy is x bar, 79.25 minus 75 divided by 25, oh, sorry, 8. The square root of 25. Yes, 2.6. I think I have this one. 2.56, yeah. Your z0 is 2.56, okay? Then your p-value is 1 minus phi of 2.56. In this case is 0.00412. This is less than 0.05. Therefore, reject H null. Okay? Any questions? Yeah, two-sided is absolute value. But this one is not. This is just the parenthesis. The reason we are using for absolute value for two-sided because it could be either from the negative side or positive side. You know, if I go back, oh, it's right here actually. If you look at the slide, it could be either from the positive side or the negative side. Remember, and the rejection region was the absolute value too. Yeah. Yes.
So there's a significant level of alpha is 0.05. If we want to use double-sided, then do we have to divide it by 2?
No. Alpha. No. That's a good question. So this is two-sided. Your alpha that you compare with p-value, you don't divide it by 2 because you already multiplied your p-value by 2. You know, that's the reason. That was a very good question. So basically, since you are multiplying your p-value by 2, you are taking care of that part. Okay? Any other questions? Okay. So this is a basically summary of all three methods for when you have you want to do for hypothesis testing on the mean of a normal population with known variance. So these are three possible alternatives. These are basically critical regions. This is testing using confidence interval, and these are the p-values. So everything in one slide. Any questions? Is it clear? This is a very good slide for your exam, crib sheet. Yep. Okay. Is there any question there? It's good. Sure? Okay. So type 1 and type 2 error. Okay. We know that we are doing basically inferences on the mean of a normal population based on a sample. Okay. We are not inspecting the whole population. Therefore, there is some error associated with this inference. If we want the error to be 0, then we should basically inspect the whole population, which doesn't make sense in reality. Okay? So there are two types of error. Let me start with a two-sided example, which is simpler. So mu is equal to mu 0, and mu is not mu 0. It's two-sided. The first type of error is as follows. In reality, the truth is H null is true, which means mu is equal to mu 0. Okay? But based on the sample that you collected, based on this sample, you reject H null. Rejecting H null means what? Z is greater than Z of alpha, for example, Z of half alpha. Okay? So this is called type 1 error, or alpha. Significance level, okay, is the same as type 1 error. So basically what it says, in reality, mu is equal to mu 0, okay? But the sample that you collected says otherwise. Okay, the sample that you collected gives you Z greater than Z alpha over 2. So your sample rejects your hypothesis. But in reality, this is true. So that's the error. What is the other type of error? Can you tell me which of these? H null is not true, and we do not reject it. Okay? That's the second type, type 2 error. We call it beta. Okay? So beta error, or type 2 error, is failing to reject null hypothesis when it is false. So basically, in reality, mu is not mu 0, but the sample that you got says otherwise. Okay? So if this is true, and this is what you get, these two gives me alpha. This is what? Beta. Does it make sense? Yep. Yeah, the sample, exactly. So it's like random sample, and you are unlucky. The sample that you got is not representing basically what actual reality is, exactly. Because it's a random sample. Oh, when you decide to go with alpha equal to 0.05, and you set up your experiment or your hypothesis testing based on 0.05, you are accepting this risk. So your threshold that you are defining is based on your alpha. Okay? So you are saying that I have a test procedure which has alpha equal to 0.05, which means every time that I'm rejecting with probability of 0.05, I'm making a mistake. That's what it means. Okay? Is it clear? Okay. So how about the off-diagonal part? What if H null is true and we do not reject H null? This is not a mistake. This is called confidence, 1 minus alpha. Okay? And what if H null is not true and we reject H null? This is called power of test, because we truly or correctly are rejecting H null, and H null is not true. Does it make sense? Any questions? And as you can see, the summation of each row is equal to 1. Alpha 1 minus alpha. Okay? And 1 minus beta, beta is equal to 1. So these are all probabilities between 0 and 1. So what is summation of alpha and beta? Anybody can tell me? Let me see who can tell me. Is what? Is what? Sorry?
It's maybe like an error rate or something?
No. No, not error rate. You won't call it. I'm saying, like, what is the number? Is there a number? Is it kind of like 1 or 2 or between 0 and 1 or maybe greater than 1? Between 0 and 1. Everybody agrees? Who disagrees? Don't be shy. Maybe that's correct. Could be greater than 1. Okay, why greater than 1? Okay, that was a trick question. You cannot have alpha and beta at the same time. Because in reality, either your H null is true or wrong. It cannot be at the same time wrong and true, you know? So you cannot have alpha and beta at the same time. Whenever you have alpha, you don't have beta. Whenever you have beta, you don't have alpha. Okay? And I've seen in some technical people make this mistake and say alpha plus beta is always 1 or less than 1 or greater than 1. It doesn't really make sense. Okay. Any question? Go ahead. At the same time. No, you could. Exactly. For a given test, you can have alpha and beta error. But at the same time, you cannot. So because in reality, either your mu is equal to mu 0 or not. But for each associated with each test, you have both alpha and beta. Okay? And as a matter of fact, you have one alpha and multiple beta. You will see in a minute. Okay. You had a question? That was okay. Any other question? Yeah. Exactly.
Beta related to?
I'll show you.
Okay.
Yeah. That's a good question. So let me start with alpha. How we can calculate alpha. Again, alpha is sort of like a probability or type 1 error. Where in different, basically, communities, they call it different things. So you may have heard false reject, false alarm, false positive, and sometimes significance level. These are different names for that. And alpha is the probability of type 1 error, which is probability is a conditional probability. It's exactly what we said here. Probability of rejecting H null given the fact that H null is true. So it's exactly here. Probability of rejecting H null given, this symbol again is given, H null is true. Okay? Which is the same as probability of test statistics falling in rejection region. Probability of test statistics falling in rejection region given H null is true, or mu is equal to mu 0 in this case. Okay? So geometrically, how we can show it? That's basically what you see. So let's say mu is equal to mu 0. That's the reality. This is H null. Okay? And this is your threshold and rejection region. So can you tell me which part is alpha? Is this part and this part. Okay? So half alpha right, half alpha left. Okay? So again, mu is equal to mu 0. This is H null. But some part of your distribution is outside your rejection limit, okay, or your threshold. So these are called alpha. So in reality, we pick alpha, okay? So we want alpha to be, for example, 0.05 or 0.01. But beta, we need to calculate that, okay? That's what we do. We set alpha 0.05, and then we can calculate beta. Any questions so far? Alpha is clear? Okay. So type 2 error. It's also known as misdetection rate and false negative. Okay? Again, if I go back, it's probability of not rejecting H null, probability of not rejecting H null, given the fact that H null is not true. So that's the same. That's here. Probability of fail to reject H null, given the fact that H null is false. Okay? Now, that's probability of test statistic not falling in rejection region given the fact that mu is not equal to mu 0. Okay? Now, look at this one. So where is it? Maybe this one over here. So your alternative hypothesis is correct. Why? Because your mu 1 is not mu 0 anymore. You see that? So mu is not equal to mu 0. So this is your distribution. So can you tell me which part is beta? Based on the definition. So that's this part. Okay? H1 is not true, which means mu is not mu 0. So what is this part? Test statistics, not falling in rejection region. Yes. Exactly. So this is beta. Does it make sense? Okay? So what happens? Mu is not mu 0, but the sample that you get, okay, says otherwise, and that's basically related to the power of test. If the power of test is smaller, your beta is larger. Okay? Any questions so far? So, yeah, go ahead. No. The same number? You said no. So put it this way. Mu 0 is this guy. When you say mu is not equal to mu 0, it should be some number. Okay? Let's call this number mu 1. Okay, for example, you say mu is equal to 50, and mu is not equal to 50. It could be 49, it could be 48, it could be 52. Okay? So that's mu 1. Okay? It doesn't matter. For now, we are talking about two-sided. If we are talking about one-sided, we are just considering left side if mu is less than, for example, 50. If we are talking about mu greater than 50, we are talking about right side. Okay? But for now, let's say both sides are okay. That's actually a good question. Now let me ask you a question. So, do you remember I told you we could have different values for beta? Why this is the case? Exactly. Exactly. So I said mu is equal to mu 0. Mu is not mu 0. It could be any number. So your mu 1 could be any numbers. For example, if mu 0 is 50, mu 1 could be 51, could be 52, could be 49, could be 48. Okay? So associated to any of these numbers, I have one beta. So based on mu 1 equal to 51, I have one beta. 52, I have another beta. 49, I have another beta. Does it make sense? Okay? So now you tell me, what is the relationship between mu 1 and beta? Look at the picture. Exactly. As you can see, when your mu 1 is closer to mu 0, it means your distribution is shifted towards mu 0. So your beta increases. So let's say this is mu 0. This is your rejection region. And let's say this is 50. Let's say this is 55. Okay? Where is the other one? So this is beta for 55. So let's say your mu is 52. Okay? Then what is your beta? Is this side. So this is beta of mu equal to 52. This guy is beta of mu equal to 55. So you can see definitely this beta is greater than this. So if you're, in reality, the distance between mu 1 and mu 0 is close, the probability of not detecting this change or not distinguishing this difference is higher. And that makes sense. Okay? So it's harder to distinguish between 51 and 50 compared to 55 and 50. Okay? And that's basically based on this figure, as you can see. Is it clear? Yep.
Change between.
No, we fixed alpha.
Okay.
So that's why I'm saying at the beginning of the test we fix alpha, and everything else is like if you want you do calculation, you do it based on beta. Okay. Any questions? Yeah. No, mu1 could be. We do not choose it. Okay. We're just saying based on this test, if in reality mu1 is this number, then that would be beta. If in reality mu1 is 55, that's the beta I'm going to get. Any other questions? Actually, that's the most important part of like hypothesis testing in terms of concept. The rest is just plug the numbers and get the basic result. Yeah.
Small value for alpha? Like if you want to increase your confidence too much, like 99, what is the trade-off between selecting 99% and 95%?
So the trade-off is, you will see, I think I have it in these slides. I don't think I get time. But the trade-off is basically, if you increase alpha, your beta decreases. If you decrease your alpha, beta increases. That's the trade-off. And it depends on basically what you want to do with your study. Okay? But in practice, usually we go with a small alpha. And if you want to decrease basically beta, we increase what? Sample size. Exactly. So that's the best way to basically decrease your error. Fix alpha, okay? Increase your sample size, your beta drops. I'll show you, actually, not today, but later on Friday, how by increasing sample size you can basically decrease beta. Go ahead. You have a question?
I guess for your experiment you choose, do you want more false positives or false negatives?
Exactly. That's the trade-off between these two. Okay. But how about having a small false positive, but again a small false negative? That's doable by just adding sample size or having more experiments. Any questions? Are we good? I'll give you 30 seconds and I let you go 30 seconds earlier today. Let's see. Yeah, that's enough.